Another application of differentiation is in optimization. Suppose that profit denoted P of producing X items Another application of differentiation is in optimization. Suppose that X is the number of items that's been produced, and P being the profit that is generated by producing the X items. In optimization, we are interested in determining how many items X that we need to produce in order to maximize the profit P. And we can determine the number of items that need to be produced to maximize P by differentiating P with respect to X, setting it equal to 0 and solving for X. Because we've previously studied that we could either maximize or minimize a function by differentiating that function with respect to a variable. So if P is a function of X and we want to maximize P, we could differentiate P with respect to the variable X which it is related to. We could do the same if we want to minimize the cost. So suppose X is the number of items that we're producing and C is the cost associated with producing those X items. So in the optimization here, we are interested in determining the number of items that we need to produce in order to minimize the costs. So as discussed previously, we could either maximize or minimize a function by differentiating the function with respect to a relevant variable and setting that equal to 0 and solving and by solving for X. Let's consider another application of differentiation. Optimization is an application of differentiation. And in optimization, we are interested in either maximizing or minimizing a variable. A typical variable that we'll be interested in maximizing is profit, which we will denote P. A typical variable that we may be interested in minimizing is cost, which we may denote C. So in optimization, we'll be interested to know how many items that we need to produce to maximize profit. Or in a minimization problem, we'll be interested to know how many items that we need to produce in order to minimize the cost. So if we want to maximize a profit P, we can differentiate the profit function with respect to X, and then by setting dP and then by letting dP dx equal to 0 and solving for X, we can determine the number of items X that will maximize the profit. Same can be done with minimizing cost. See, the cost is a function of X, the number of items being produced. If we differentiate the cost function with respect to X, and if we let it equal to 0 and solve for X, we can determine the number of items X that will minimize the cost. So let's look at an example of maximizing and minimizing variables. Example 13. If the cost of producing X number of items is given by C, where C is X on 10 minus square root X plus 10, how many items need to be produced to minimize the cost? So cost is a function of X, X being the number of items produced. We want to find how many items we need to produce to minimize the cost. So we start with differentiating C with respect to X. So derivative of X on 10 is just 1 on 10. Derivative of minus square root X is minus X raised to the power minus a half. Derivative of 10 is 0. So we now let dc dx equal to 0 to find the value of X that minimizes C. So from that we obtain 1 on 10 minus a half X to the minus a half equal to 0. This gives us 1 on 10 equal to X to the minus a half on 2. So this cancels out and we get 5. So we have 1 on 5 equals 1 on square root X. This implies square root X is 5. It also implies X is 25. So we need to now figure out if X equal to 25 in fact minimizes the cost C. So let's do a test. So let's put X below this horizontal line, dc dx above the horizontal line, and when X is 25, dc dx is 0. For X less than 25, so if we substitute, for instance, 24 in this expression, we'll obtain a negative answer for dc dx. And if we substitute a value greater than 25, for instance 26, we'll obtain a positive answer for dc dx. So in fact, X equal to 25 minimizes C. So the number of items that will minimize the cost is X equal to 25.